this.
Not that you can, but I'm just thinking specific things that you can input. I'd rather study more on that.
So what was that parabola that I had it on the board at the end of class, but we didn't get to it? Can somebody tell me what the equation of that?
Y squared plus 12y.
Hold up. Y squared
Plus 12y.
plus 12y.
Plus x. Minus 1. Equals 0.
Okay, and we had completed the square on that already?
Yeah.
We did?
Yes.
Okay, so we had gotten it down to y plus squared.
Plus,
Wait, no, that's not right, right?
yeah, plus x equals 37.
So that's where we were? All right, so we're going to talk about parabolas, and then I think we're going to start talking about the final. Okay? So at the end of class, I had this equation up here, and I tried to complete the square, and we have been talking about ellipses. Anybody need a copy of this from last class? Yes? Mm-hmm. Oh, by the way, today I have to, after class, normally I go to my office, but today I'm substituting for faculty that's out sick. So I will not be in my office after class today, just so you know. Okay, so I had this on the board, and then we completed the square, and then we looked at it, we said, wait a minute, this doesn't look like an ellipse, because to have an ellipse, you had to have both of your variables squared in the problem. And here the x is not squared. And I said, well, then it must be something else. And we flip over and we see that we have general equations for parabolas. And there's 4 of them up there. I'm only going to write one of them down here. Y minus k squared equals 4 times, 4a times x minus h. So that's the first one there, right? And it says that the vertex of this parabola is hk, the focus is h plus a comma k, the directrix, which we haven't even talked about, is x equals h minus a, and that the axis of symmetry is parallel to the x-axis. In other words, it opens to the right. So it opens like this, all right? That's the equation. Then there's three more after this, right? Y'all see that? So when we look at this over here, does it look like that one, or does it look like the one below it? Let me see. This is y minus k squared equals negative 4a, and then x minus h. This one is the same thing, but this one opens to the left, like this. Okay, so we have to determine which of these it is. Do you see why I'm not looking at the 2 below that? Why am I not looking at the 2 below that?
Because they're x's.
Because those have the x part that's squared, right? So when your x is squared, it opens up and down. When the y is squared, it's going to open left or right. All right, so it's one of those. Let's try and make it look like that. So let's move the x to the other side. How about we do that? Okay, so we get y plus 6 squared equals negative x plus 37. Now both of these have a 4 out in front, right? A 4 in front. And then there's an a, which we haven't determined. And then we have to have in both of these x here, right? X.
So you have to extract a negative 1.
So we're going to need to extract a negative. Let's do that. Let me try slowly to do this. Y plus 6 squared equals, let's pull a negative 1 out, and that'll give us x minus 37. Y'all okay with that? So it's looking more like this one, isn't it? Than this, because this one has a negative out front, this one doesn't. All right. I have to have a 4 here, and then some number. But when I put those together, it needs to be 1. So how about this? See if this makes sense. Negative 4 times 1/4 x minus 37. Now that's a little tricky, but do you see that? Negative 1 is the same as negative 4 times 1 over 4. A fourth of 4 is negative 1, right? Or a fourth of negative 4 is negative 1. So what I'm trying to do is I'm trying to like massage this number into that format. So does this match up now? Pretty much exactly. Does it match that? Yes? Okay. So can you tell me what the vertex of this thing is? What's the vertex of this parabola? Well, it should be HK, right? HK? So what is H for us?
37.
37? Are y'all reading off this thing here? Vertex here, HK. So my vertex is 37 what? Negative 6. See, in the formula, there are minuses here, which means that you go with the opposite of the number you see. So if you see negative 37, you're going to put positive 37. If you see positive 6, you put negative 6. So that's our vertex, right? Now, the focus in the directrix. Let's just see if we can figure out what they are. The focus, and then we'll talk about what they are graphically. The focus is, according to the formula, H minus A. What was A for us? I don't think we ever determined what A was. What was A? That's A. A is 1/4, right? So the focus by the formula is H minus A K. So that would be 37 minus 1/4, negative 6. (37 minus 1/4), you could get a common denominator there and put those together, right? What about the directrix? Again, we're acting like we don't know what it is right now. This is going to be H plus A, which would be 37 plus 1/4. Questions right now? What I've done? What is that common denominator? Where did my calculator go? I have to multiply 37 by 4 here real quick. So this is 148 over 4 minus 1. So this becomes 147 fourths minus 6. And this one becomes 149 fourths. X equals 149 fourths. Do y'all know where I'm getting those from? This? Just subtracting, getting common denominator, and then adding. All right, so let's see now if we can graph this. And I'll explain the focus and the directrix as I'm graphing it. This is a parabola which opens which way? Does it open up, down, left, or right? Opens to the left. We know that, right? Okay, the vertex is the point 37, negative 6. So that means I'd have to move out 37. So let's say that's like 10, 20, 30. Let's say that's 40. So 37's about here, and I go down 6. So there's my vertex. This thing opens up like this from here. So it's going to go like this, like this. Now, the focus is this point 147 over 4, negative 6. Which, by the way, this is 36.75, right? So that's really close to this, isn't it? It's just barely to the left of this, like right there. I'm going to make it a little smaller. And then your directrix is x equals this number, which is a little bit bigger than 37. And it's x equals a number, which means it's a vertical line. So I'm going to draw a dotted vertical line like this. Okay, now I'm going to zoom in on that. Okay, I want to zoom in to help illustrate what those things are. So what you have with parabolas is this. You have a vertex, and your parabola opens this direction. Then you have this thing right here called the focus, and then you have this dotted line over here, which is called the directrix. The distance from the focus to the vertex, the horizontal distance here is equal to the horizontal distance here. So the distance that these are from one another is the same as the distance as these are. All right? So what is the relationship between the directrix and the focus? Like how does it factor into this? Why do we have this thing called a directrix and a focus? So here's the idea. If I were to measure the distance from the focus to this point, that distance is equal to the distance horizontally over to the directrix. And that works for any point. So the distance from here to here is equal to the distance from here to here. And that's how we define a parabola. It's not important. I'm not going to test you about it, but that's why this line and this point are important. It basically, all you need is the focus and the directrix, and you can define a parabola. So what I'm going to ask you to do is start with an equation, get it into its standard form, and then identify the focus, the directrix, and the vertex. So I'll start a new problem here in just a second from scratch, and we'll do everything, but I wanted you to at least see a picture. Now, why is a focus important in a parabola? Do we use parabolas in the real world, do you think? Have you ever seen a parabola in the real world? You're what? Where have you ever seen a parabola? No? Other than in class, yes. Other than in class. In the real world.
Like in
Glasses?
focusing, you have to know that for.
Okay, so you have your lens is something maybe parabolic. Do any of y'all use these things? No? This is a cell phone. No? Cell phone? How do we communicate electronically? When you send signals out, right? You make a phone call. There's waves that you can't see, right? It's invisible to our eyes, right? But right now, if we could see the things coming out of our phone, the electromagnetic waves coming out of this, if we could see it, we would all be blinded. Because it's everywhere, right? It's coming out of your phone. It would be everywhere in the room. You'd be trying to see through. You couldn't get through it. It'd be completely blinded by it, right? But it's everywhere. So those signals are being sent out. So here we are. You're sitting here with your little phone, right? Or your big phone, whatever you want. And it's sending out this electromagnetic radiation in all directions. And somewhere out there is a tower. Somewhere around us, there's a tower. And up on that tower, it has these, you may have seen them, there's like these little boxes that go around them. And those boxes, if you were to like open them up so you could see what's inside of them, the box would look like this. So this is not a very good picture at all. That's not a good picture. But basically the inside is parabolic, all right? It's got like a little curve inside of it. You've seen these in other places. People have houses or apartments and they've got this dish sitting out there, right, to get their cable TV. Y'all seen those? Those dishes are parabolic. And they have a little thing sitting here. Y'all seen that? Same idea here. You've got this thing, it's parabola, and you've got this bar in the middle. And what happens is any electromagnetic radiation that is being spewed out, when it hits here, it's going to reflect. And when it reflects, it's going to hit the focus. It will hit the focus. And it actually does not matter where it comes from. It's always going to go to that point, no matter what. Because of the shape of the actual shape of the parabola means everything will bounce to one point. And the one point it bounces to is the focus. Does that make sense? So what you can do is send your signal out everywhere and have this little thing receiving it, and the parabolic reflector will focus the signal to a point, and then that point says, okay, you know, there's my data, and then it sends that out, and it transmits that. So this tower receives your dialing your phone, you know, and you send a call. This receives it. It sends that out everywhere. And then there's another tower sitting over here that receives that and then sends that out everywhere. And it just keeps relaying it from tower to tower. And then the person you're calling is sitting there, and their tower, wherever they are, with their phone, their tower next to them eventually gets that signal and spits it out to you. And then you start talking or texting or whatever. And it all happens the speed of light, right? So the parabola is absolutely essential for communication. We have to have a way of gathering the electromagnetic radiation and focusing it into one receiver and then retransmitting it out. So we use it all the time. You also use this every time you drive your car at night and you turn your headlights on. When you have your headlights, you know, you turn them on. If you've ever been like in the fog or something, you can actually see the beam of light, right? And all your headlight is a light bulb, and then a parabolic mirror around it. And what happens is the light comes out, hits the parabolic mirror, and it's the reverse of this. It spits it out straight, like this. Okay, so all the light coming out in all directions gets focused into a beam and goes out. Now, you can make an adjustment. If you've ever seen like a flashlight where you can adjust the beam and spread the beam out or focus it, all you're doing when you turn that knob is you're either moving the mirror back and forth or you're moving the light back and forth. And what you're doing is you're changing the position of the focus. If you change the position of the focus, it has the effect of saying, oh, wait a minute, instead of sending everything straight out, it's now going to change that reflection angle, and it spreads your beam out instead. But all you're doing is manipulating the focus of the parabola. So parabolas are everywhere, all right? That's why this point is an important point for us. And we want to be able to recover the focus from an equation. If that makes sense. So if someone gives us an equation, we want to be able to recover the focus. All right, let's do an example from the beginning. So I'm going to pick one here randomly. Let's do this one. We have x squared plus 6x. When you see x squared plus 6x, right now you should be thinking this is either going to be an ellipse or a parabola. The parabola is either going to open up or down. If it's a parabola, it's going to open up or down because the x is squared, right? All right, and then now minus 4y plus 1 equals 0. All right, so you look at that, and what I would ask you on the final is something like, identify this as a parabola or an ellipse. If it's an ellipse, give me the standard form, the equation of it, right? and I might ask you to sketch it. If it's a parabola, find the vertex, the focus, and the directrix, and draw a quick sketch of it. So we are going to say this is parabola, right? And we know that because only one of the variables is squared. So we know that right away. We just need to figure out which of those four forms it is. And you can already tell me it's going to be one of the bottom two, right? So it's going to open up or down. All right, we got to figure that out still. So how are we going to do that? What's my first step? Complete the square. So I've got to complete the square on this piece right here. So that means I'm going to take half of 6, which is 3, and square it, which is what? 9? So I'm taking half of the 6, which is 3, and I'm squaring it, which is 9, and I'm going to add and subtract 9 at the same time, right? So this becomes x squared plus 6, adding the 9, subtracting the 9. That's that hidden 0 that we've done several times now. And then I still have minus 4y plus 1 equals 0. Now the first 3 terms are guaranteed to factor. What will they factor to be? What's that going to be? X plus 3 squared. X plus 3 squared. And then the rest of it I can put together. I have minus 4y and then minus 8 equals 0. Is that all right, everyone? Okay. Am I? Yeah, I'm good. All right, I'm going to move the y stuff to the right-hand side in the 8, right? This stuff all to the other side. And that's going to make it positive. And boy, this is starting to look a lot like one of these two here. What do I still need to do? What do I still need to do?
GCF.
I need to pull out. The way you should look at this is you need this y to be a 1y. Okay? That's what you need. You need this to be 1y because in the formula, you're either going to have 4a and then y minus k, or you're going to have negative 4a and then y minus k. And the key here is that there's a 1 in front of these y's, right? So if this had said 3y plus 8, 3y plus 8, you would have to pull a 3 out. Even though 3 doesn't come out of here, you would have to pull a 3, which means this will become 8/3 if you pull a 3. So it's not quite GCF. In this case it is because 4 comes from both. But really what's forcing you is to make this a 1y, okay? So I'm going to pull a 4. That'll give me a y plus 2. And I think we're looking like this one, aren't we? We don't have a negative out there? And if that's the case, what's a for us here? The formula says we have to have 4 times a number out front. 4 times a number. So the number's got to be 1. All right, so we're going to look at this as being x plus 3 squared equals 4 times 1, y plus 2. So this 1 is our a, isn't it? The 1 is the a. Which way does this parabola open? Opens up? Opens up. So once I've gotten to this point right here, I know that this parabola opens up. Does anyone have a question? I want to make sure, like now's the time, ask.
So you don't really care that the formula says y minus x inside the parentheses and so y plus
Wait,
something?
y minus what?
Oh, in the parabola, inside the equation, it has
Y minus k?
y minus k.
Right here?
Y minus k.
It's okay.
It's okay that it's not a negative.
That's right, because you can always look at that as being y minus negative 2. Right? So it is a y minus k. It's y minus negative 2. So k is going to be negative 2. Make sense?
Yes.
I kind of see what you're saying, because if you're trying to make it look like y minus k, you might have wanted to pull a negative 4 instead.
Yeah, and that would have been a bad thing.
That would have been bad because it would have made the y negative. This right here would have been negative, which doesn't match the formula. That you can't have. Good?
It changes your quad, it changes the whole thing.
Yeah, it changes it.
Yeah.
The only way that it'll open up is if that's a 1 in front. If that's not a 1 in front, then it'll open the other direction. Okay, I'm going to graph. Or should we identify the vertex? Let's identify everything first. Vertex. My vertex is HK. So what is H and K here? -3 from this, and then from this, -2. Now our focus, I'll write the formula down just so you know which one I'm using here. Our focus is H and then K plus A. So that'll be -3 and then K, which is -2, plus A, and A was 1, wasn't it? So this is going to be -3, -1. And then our directrix, which is a line, is y equals, and this will be K minus A. So -2 minus 1, which is -3. All right, graph time. Let's start with the vertex. -3, -2. By the way, I would provide you with this on the final. In fact, keep it, bring it to the final, all right? Yes? You don't have to memorize all those, yes.
I just stuck that one. I have that extra one. I do want to do examples on it.
Did I write something on it?
No.
Oh, you were writing on it.
Yeah.
Oh, okay. trying to cheat over there, I guess. Okay, so there's our vertex, right? Our focus is -3, -1, which is here. And our directrix is, in this case, a horizontal line like this. Now let me try and show you. You don't have to pay too much attention to this when you're doing this on the test, but again, trying to illustrate how you draw a parabola given the focus and directrix. The point here in the middle, what I'm doing is I'm measuring the distance from the focus to the directrix, and I'm taking the halfway point. Okay? Yes? Then let's just pick a length here. So I'm just going to pick this length right there, okay? From here to here. And what I'm trying to find is where the distance from the focus to the end of this, I'm going to guess right here, that distance is the same as the distance here to here. Nope, not quite. So I need to move it up. So maybe about right there. So distance from here to here, focus to here, is the same as the distance from here to here. Do y'all kind of see that? This point will lie on the parabola. So I know my parabola goes something like that. And I could do the same thing on this side, and it would go like this and open up. That kind of makes sense. That distance measurement is what kind of controls how narrow and wide it is. I'm not going to care about that. I'm not going to care. All I care about is you identifying the focus, the vertex, and the directrix. And More importantly, I want them over here like this. And then you're drawing, just make sure that things in the right place. Is that okay? Does that seem all right to you? So to give you an idea of where you might see this later on, okay, for those of you who might be curious as to why you would want to be able to graph a parabola or an ellipse quickly, is something like this. Let's say you had look at this right here. X squared over 4 plus y squared over 9 equals 1. Do you know what that is if you graph it? What is it? What is that? That's an ellipse, right? You have the x squared and the y squared. They're over something equals 1. So that is the ellipse from last class, isn't it? Yeah? Okay. I'm going to do something here. I'm going to change this 1 to a third variable, z. Now what is this? Well, this changes everything because we have a new variable, right? So check this out. I'm going to try and draw something for you here. This is our standard xy axis, right? That's our standard xy axis. Imagine that we're going to take that and lay that on the ground. And when we lay it on the ground, we're going to create a third axis that's going to come out of the page like this. And that's going to be my z-axis, right? And let me draw that for you. So here's my x and y laying on the ground and my z-axis coming up. Can you kind of see that three-dimensional look to it? Yes? Again, you're not going to be tested on this. I'm just trying to get you to see what's going on here. All right, what if z was 1? What if z was 1? If z was 1, what would we have here? If z is 1. We'd have that ellipse, wouldn't we? Wouldn't we have that ellipse? And it would look something like, so imagine back here, if that was a 1, we would have drawn this. It would have actually gone like this. 2, -2, 3. That would have been the ellipse had that been a 1. That's the way we would have drawn it. That's what we did in this class, right? But in a later class, you're going to be dealing with this thing, and you're going to be trying to figure out what this looks like. So what you do is you first start off by letting z be 1. If z is 1, then you have this picture, right? So imagine, here's your x, your y. If z is 1, that means I moved up off the piece of paper 1 unit. Can you imagine that? Moving up off the paper 1 unit and then drawing that ellipse. So it's almost like this ellipse lifted off this sheet, raised up 1 unit. Yeah? That would look like this. It's kind of lifted off the sheet of paper. Can't tell it's lifted off the sheet of paper, but it is. All right? What if z was 0? What if z was 0? That means I'd be down on the sheet, right? But what would this equation become if z is 0? Just look at it real quick. X squared over 4 plus y squared over 9 equals 0, right? So let me multiply both sides by 36. That'll clear my fractions out, won't it? It'll clear this out. So multiply this by 36 and you get 9x squared, plus multiply this by 36, you get 4y squared equals 0. What is the only number that you can plug in for x and y to make this true? 0, right? Both 0. They both have to be 0. X has to be 0 and y has to be 0 for this thing to be equal 0. So that means if z is 0, x and y both have to be 0, which means you're at the origin, right? You kind of following this? Then you say something like, let's let z be 2. If I let z be 2, it's going to be an ellipse still, but it changes because I need to get rid of that 2. So what I do is divide, and I make this an 8, and I make this an 18, and that's back to a 1. See, what I've done is I've taken the 2 here, and I've doubled both of these denominators. Now that's going to change the ellipse. So now when I've raised up 2, I have a different ellipse up here. It's actually a little bigger. And then I can keep doing this. I can keep changing my values of z, and I start drawing these different ellipses at different levels. Can you all kind of imagine that? At each level of z, I'm going to have a different ellipse. These are called level curves. And when you put them all together, what you're going to get, if you were to keep doing this for different values of z, is you're going to get like an egg, like a 3-dimensional egg, and it's called an ellipsoid. Does that make sense that you would get that? You just keep on drawing different ellipses at different sizes, and eventually it'll go back to a single point on top. So you got like a single point on the bottom, single point on the top. I can't draw a real good egg 3-dimensionally. It's hard to do. But what you can do is start stacking your level curves to get an idea of what it looks like. Does that kind of make sense? That's what you would have to do in Cal 3. They're called level curves of surfaces. So these are 3-dimensional surfaces. Okay. Let's talk about the final. I think we're done. I think we're done. Yep. Yeah, we have to have a final. We don't have. You don't have to. As my dad always said, you don't have to do anything. We'll have a pizza party. A pizza party. Ellipse pizzas.
Project finals with food.
How much larger is this slice?
All right. Well,
The angle.
Where's your focus?
we have an hour, and then we have all of Thursday, right?
Switch, that's all I have to say.
Is there a book at every table? Does every table have at least one textbook? I don't know. This is like 75 problems, probably. This is probably in the neighborhood of 75 problems. So what I think we should do is perhaps pick a section. So I'm going to take requests here. And hopefully on Thursday you will have a better idea of what to ask me. My thing is this. I'm gonna test you on concepts from this group of questions. If it's not in here, it's not on the test. All right? But I'm not going to test you on every concept in here because then I can't make a 75 question test. There's not enough time, and I don't want to grade it, right? So what I did is I went through each section, and I said, all right, what problems from each section would I put on a test? And these are the ones I would. So let me tell you what each section is about, and you stop me when I get to a section you'd like to see a problem from. So 2.4 has to do with circles. And the problem specifically here is where you're going to have to complete the square a couple of times. So shall I move on? Well, for both, you have to do it for both the x and the y. Like you have to complete them both. 7.1, angles and their measures. that had to do with like linear speed, circular motion, area of a sector.
Let's do that.
My downfall starting at 8.
I would like if you had a quick problem.
From where? 7-1?
Yeah, just because that's a good review of the art.
Yeah, so let's see, on 7-1, whoa, page 5, yeah. 516.
It's too easy for you guys.
So I'm looking at page 516, and I've asked you to look at numbers 95 and 99. So 95 is watering a lawn and trying to find the area. And 99 is object is traveling on a circle with a radius.
99.
99 is probably the one you want. So do you want me to actually do 99 or?
One like it.
I don't care. It's your call.
Let's do it.
Do it? Okay. 99, motion on a circle. An object is traveling on a circle with a radius of 5 centimeters. Radius, 5 centimeters. An object is traveling on this circle. If in 20 seconds a central angle of 1/3 radians is swept out, in 20 seconds, an angle of 1/3 radians is swept out. What does that mean?
Covers that much.
Okay, so they're talking about central angle. So this thing's moving around this circle. Doesn't matter if it's clockwise or counterclockwise. It's irrelevant. But it says that in 20 seconds, it will sweep out an angle. This angle right here will be 1/3 radians. And it takes 20 seconds for that to happen. So that kind of tells you how fast this thing is moving around the circle, right? Okay, so let's get to the question. What is the angular speed of the object? What is the linear speed of the object? Okay, so question, first part, angular speed. Part B is the linear speed. So what is the angular speed of this object? What is the definition of angular speed? It's theta over time. And we call that omega. So we need the angle that it's going through divided by the time that it takes it to do that. And aren't we given both of those pieces of information? The angle that it sweeps out is 1/3 radians. And it does that in how many seconds? 20 seconds. So all you have to do is divide 1/3 by 20. And your answer will be in radians per second. So this is going to be 1/60th radians per second. Don't make it more complicated than it is, right? It's the angle you sweep through divided by the time it takes you to do it. 1/3 divided by 20 is 1/60th. Now, linear speed requires a little more work. What is the linear speed? There was a formula for it. Anyone know the?
Equals radius delta.
Say again?
Isn't it radius delta?
We called it V, right? Yes? R times omega was one of the formulas. It's the radius times the angular speed, which we know that the radius is 5 centimeters times, we just got 1/60th radians per second. And you can reduce that fraction. It's 5 over 60, which goes in there, what, 1/12? 1/12 centimeters per second. Because it's a linear speed, it has to be distance over time, like length over time. Is that sufficient?
Converted in a miles per hour.
It doesn't ask for that, right?
No.
Yeah, okay.
How are you gonna ask?
No, I don't think so. I don't think so. You're requesting it? Yes, okay, we will. We have a request to convert that to kilometers per millisecond. So, no. Yeah, light years. All right, I guess we can check that one off. There's no way I can work 75 problems, right? So we just need to kind of pick. How about page 528, which is number 69, which is, interesting.
Right triangle through the
Other requests here? Should I give you some time to look at this right now, or do you just want me to, like, what do you want to do?
Can you go over, hold on now, give me some.
Let's see, it's 11:48. We have till 12:40. So why don't we take like 10 minutes for you to just kind of look through this and breeze through your book. Anybody need a book? Y'all want an extra book over there? Why don't you just kind of look through the review, look through the book, and then find anything that you really feel like you would like to talk about right now, and then we'll do that. So let's say at noon, okay? At 12 o'clock, I'll kind of open up the floor to questions.
Until then, you can do some.
I'll wait 10 minutes. I'll wait because I don't want to distract people. Just go pick a few things you want to look at, circle them, and I'll start with you. By the way, there will be an emphasis on the stuff that we have not been tested on.
Okay.
All right, so like there are things that you have not seen on test yet, right? Like polar, partial fractions, vectors, a little bit of vectors, right? But polar, partial fractions, ellipses, parabolas, those will be for sure in there, for sure. The other stuff is going to be things I pick. What do you got?
Okay, so 7.6, number 20.
Okay, hold on.